Hey stats students, I hope you guys are doing great. Before we get into our notes, I want to use Excel here, what I've created to kind of get you an introduction to what we're looking at, what the main concept is. So what I have here is I have 20 numbers, and let's assume that's the population. That's all the numbers in some set. Okay, I don't know what these numbers might correspond to, but imagine that they're not heights because these numbers wouldn't make sense, but they're the heights of 20 people in a room. Okay, or they're the length of 20 people in a room's shoes, something like that. All right, so it's everybody, it's the whole population. Okay, now, hey, I'm showing you the entire population. Okay, but what we're going to be looking at today is how we can use a sample to make an inference about the population. We use a sample, okay, use the statistics from a sample to make some sort of statement about a parameter of the population. Remember, statistic goes with sample, parameter goes with population. So like the mean, X bar, we know is the mean of a sample. Mu, we know is the mean of a population. Okay? So let's just pretend that we don't know all 20 numbers, but we're going to randomly select a couple objects from it, and we're going to look at their mean. So I'm not going to get out my random number generator. I'm just going to grab some here, but assume that this is random. Let's say I randomly grab this number and this one. Okay. Now remember, I don't know what all 20 numbers are, but I randomly selected 2 out of that population, and these are the numbers that I got. Well, I might be interested in what the mean of these 2 numbers are. So I can use Excel to help me find average here. And we're going to find the average of those 2 numbers. And it is, oh, sorry, that's so small, 14.6. So this 14.6 number right there is the average from the sample of size 2 that I took. So I hope you would agree with me that 14.6 would be an approximation of the mean of the entire population of all 20. We selected 2, we found the mean of those 2 to be 14.6, and I would estimate that the population mean is about 14.6 because that's all the information that I have. How could I get a better approximation of this? Well, instead of there we go. Instead of selecting 2, what if I selected 4? All right, so here we go. Let's pick that one. Again, this would be random if I was doing this the right way. Whoops, I just changed that number. So now I selected 4. Okay. All right, so let's find the mean of those. There you go, and I get 12.425. Let's make that a little bit bigger, easier to see. So now I'm estimating that the mean of the population is 12.4. Which estimate am I more confident in? Okay. I hope you would realize that I'd be more confident with this estimate because I selected a larger sample size, right? It's possible if I select 2 that I might just, by random chance, select 2 of the highest values. Like if I randomly selected 2, I could end up with those 2. And I could say my estimate for the mean is the average of these 2, which would be what? 16.45, right? Notice how different that is from this one. When I select more, what happens with those extreme values? They kind of get averaged out, don't they? Okay. So this is our concept, right? We've got a population. We're going to take a sample, and we're going to find the mean of that sample, and that's X bar. And X bar is our estimate of the population mean mu. Okay. That's the concept. Okay. Now we're going to talk about levels of confidence. Like I said, the larger the sample size, the more confident I am going to be in my estimate. Okay. But how do I handle that? And how do I describe like more confident? Okay. What we're going to actually do is we're going to create a range. So let's say my estimate for the mean is 12.4. But I might want to make a statement that I am estimating the mean of the population to be between 12 and 12.8. See what I did there? I subtracted 0.4 and added 0.4. I've created this range of possibilities for the population mean to be in. And what we're going to end up doing by the end of today is we're going to say things like, I'm 90% confident that the population mean is between 12 and 12.8. Okay? Or maybe it's 95. Maybe I'm 95% confident that the mean is between 12 and 12.8. Okay? So we find the X bar. We take a sample, we find the X bar, and we develop this range of confidence. Okay? The more confident I am, okay, think about this. Well, I'm going to wait. I think that might be too soon to make that statement. All right, let's be careful. So let's go on and talk about some things. So this is section 6.1. We're finding confidence intervals for the mean. Okay, and here are some assumptions that need to be met here. We have some random variable x. Okay, we are randomly selecting our sample size, okay, of size n from a population. We are assuming in this case that we know the standard deviation of the population. Okay, that's going to be important. So today we're starting with assuming we know the standard deviation of the population. So in other words, we don't know the mean of the population, but we do know its standard deviation. Okay. Now, what we're going to do will work is if the X distribution is normal, it works for any sample size. I can take a sample size of 2, 10, or 500, and this method will work if we know the distribution of our random variable x is normal. Okay. However, if we don't know what the distribution of the population looks like, we have to take a sample size greater than or equal to 30, a sample size of at least 30, and that should sound familiar to you from what we looked at last chapter. Okay. So if the distribution is unknown, we need a sample size of at least 30 to be able to do this. Okay. Now I talked about using X bar to estimate mu. Okay, that's called a point estimate. A point estimate of a population parameter is an estimate of the parameter using a single number. So X bar is a point estimate of mu, and we'll talk about other point estimates here, but we're really focusing right now on estimating mu, the population mean, and X bar is that point estimate. Okay. Now, whenever I'm estimating mu, I'm taking a sample, I'm finding an X bar, and I'm saying X bar is my estimate of mu, but there's always error in that, right? There's no way to know exactly what the population mean is unless we can have access to the entire population and find that's mean, okay? So when we give our estimate, because there's a margin of error, we could be off a little bit, okay? We want to be able to say our estimate with a certain level of confidence, such as 90%, 95%, or 99%. Those are our confidence levels. We're going to use the letter C for how confident we are. All right? So, for a certain confidence level C, we need to find the Z-score. It's called the critical value. It's Z sub C. Okay? And that is the number such that the area under the curve between the critical value Z sub C and negative Z sub C is equal to C. Okay. So what does that look like here for us? Okay. So what we're going to find, okay, and let's pick a confidence level such as like 95%. That's our confidence level. What we need to find is Z sub 0.95 and Z of negative 0.95. And what that means is we are finding these z-scores here. Oops, I put my negative in the wrong spot there. There we go, in front of the z. We are finding the z-scores that we end up with 95% of the area under the curve is between those two z-scores. If we're going to find a confidence level of 90%, we need to find the z-scores so 90% of the area under the curve is between them. Okay? Or same for 99%. 99% of the area is between them. So that's what this critical value is. It's a z-score that 95% or 90% or 99%, whatever our confidence level, that percent of the area under the curve is between the z-scores. Okay? So, okay, we have some very commonly used z-scores, 90%, 95%, 99%. Now, you could do something different. You could do 80%, 85%. 97.5% if you want. But these are our three most common. So we need to find the z-scores for these three. Okay? We need to find the z-score for 0.9, 0.95, and 0.99. When we have these, you'll want to have this written down so that it's easy for you guys to find and reference. Eventually, you'll probably have them memorized because we'll use them so much. But have these handy. So how do we find that? Well, let's start with 90%. We need to find a z-score that has 90% of the data between. Now, we've found z-scores from percentiles and things like that. So we're working backwards here. Okay? So what we need to do is we need to start with our table, okay, and then use the table to find the z-score for the area that we desire. All right, so we've done this before. But now we have to be a little bit careful. When we did percentiles, we could just look up our area because the area in the table gives only to the left, all the way to the left. Whereas now we're finding the area between two. So how do we do that? Well, let's break this down a little bit more. If 90% of the data is between these two z-scores, okay, what percent of the area is outside? Well, this would be 0.05, and this would be 0.05, right? 5% and 5%. That gives us our 100%. Now, when we look up using the table in the back of our book, it's only area to the left. So what I could do is I could look up 0.05, find that in my table, and find the z-score that corresponds to 0.05. Or I could look up what? To the left of this one would be 0.95. I could look up 0.95 in my book to find this one. So let's do that. Grab your table. Okay, make sure that you're finding the same values that I am. Okay, I'm going to look up 0.05. Okay, this is going to be a negative z-score, of course, because we're to the left of the mean. If I look up 0.05 as my area, I see a 0.0495 and a 0.0505. Okay, and I see that to be at negative 1.6, and if I split the difference here, I'm going to say it's negative 1.645. Oops. Okay, so this is negative 1.645 for that negative z-score, which tells me this z-score should be at 1.645. Okay. And when I look up 0.95 in my table, I should end up with the same thing. So I'm looking up 0.95, and I'm seeing 0.9495, 0.9505, halfway between them is at 1.645. Okay? So we just found our critical z-score for 0.9, or a 90% confidence interval, as 1.645. All right, now what I want you to do, see if you can find the z-score for 0.95. Okay, if you haven't done so, pause your video, see if you can do this. All right, so here's how I'm doing it. Okay, 0.9, 95% of the area is between these two. Let's see, to me that means there's 2.5% here and 2.5% over there. So I'm going to look up 0.025. 0.025. And I see that right at negative 1.96. So this is negative 1.96. This is positive 1.96. Our critical value for a 95% confidence interval is a z-score of 1.96. Okay. Go ahead and pause the video, find it for 99%. All right, so 99% means I need 0.5% here and 0.5% there. So I'm going to look up 0.005. 0.005. There we go. I see 0.0049. I see 0.0051. Okay, so I'm going to take what's halfway between those, negative 2.575. Why did I say 2.575? Yep. And this is, there we go. So our critical z-score for 99 percentile is 2.575. Awesome. Those are important. We'll need those. Make sure that you have those written down. If you haven't noticed yet, there's a little table in the bottom of the page that we were just looking at to find z-scores that give those confidence intervals. All right. So let's keep moving forward here. Okay. Now, remember, x bar is an estimate of mu. Okay. There is a margin of error. So how do we calculate that margin of error? Remember that in this, I said, okay, well, maybe our estimate is 12.4, but we're going to say it's between 12 and 12.8. All right. How do we calculate that? How do we find that margin of error? Here is our formula. Our error tolerance is how far off we could be in either direction, to the positive, to the negative side. Okay. Our error is calculated by taking our critical value, our z-score corresponding to the confidence interval that we have, and multiplying it by the population standard deviation. Remember in our assumptions, okay, that we are assuming that we know the standard deviation of the population. We know mu. No sigma. Sorry, wrong Greek letter. We know sigma. Okay. So we take the population standard deviation and divide it by the square root of n. Now this might look familiar to you. When have we taken sigma and divided it by the square root of n? That is the standard deviation of the x bars. Okay. So what we're doing is we're taking the z-score that corresponds to our confidence interval and multiplying it by the standard deviation of the x bars. If you think about that for a little bit, that makes sense. Remember that we have an x bar distribution. Okay, when we have a population, that x bar distribution, okay, is all possible x bars that we could get from that population with a certain sample size. All right, we have a certain sample size when we're doing this estimate. We're taking a sample size n from our population and calculating an x bar. So it makes sense that we are using the x bar distribution. This is similar to the problems where I'd say, okay, if the mean of the population is 10 and the standard deviation is 1, I asked you questions like, what's the probability if I take a sample of size 5 that the mean of those 5 is greater than 10, less than 10, greater than 11, less than 11, between 9 and 11, those type of questions that we did last chapter. So here's what we do. Okay? Remember that x bar is our approximation for mu. So we have our point approximation for mu. What we then do is we add, okay, the error and subtract the error from our x bar to create this confidence interval, this range. Okay? So we can say that that mu is between the x bar minus the error that we've calculated and x bar plus the error that we've calculated. All right, let's get to an example here. Okay. Julia has been jogging over a period of several years. She usually jogs 2 miles per day. The standard deviation of her times is 1.8 minutes. She has a random sample of 90 times in the past year. For this sample, the mean x bar is 15.6 minutes. Find a 95% confidence interval for mu. All right, so she usually goes for this jog like every day, right? And over the last year, she's taken 90 of them. She hasn't taken all of them. If she did it every day, there'd be like 365, right? Actually, this is a leap year, 366 jogs. She didn't take the whole data set. She took a random sample of 90 of them, and that had a mean x bar of 15.6. So this is the mean of the 90. So I'm going to write this down. X bar equals 15.6. So our estimate is that mu is 15.6. The mean of all 366 jogs is 15.6. Okay. But how confident are we that the 90 that we pulled really matches what the whole population distribution is? Okay. Now remember our assumptions. Okay. Our assumptions are that we have a simple random sample of size n from a population. That's what we have. We said they're randomly sampled. The standard deviation of the population is known. Notice I gave you that. We know that the standard deviation of the population is 1.8 minutes. I'll talk about that later, okay? If you're having some issues on how we would know that, I'll talk about that later. Okay? So we've got a random sample. The population mean is known. Okay? What else? If the X distribution is normal, methods work for any sample size. Do we know, okay, that of all of our jogs in the last year, all 366, that they form a normal distribution? There's nothing in here that tells us that, right? Okay. However, we do have a random sample of 90. And we say if we don't know if the distribution is normal, if we're using a sample size of at least 30, we can do this. All right? So we've met the criteria. Okay? It's a random sample. Population standard deviation is known, and we have a sample size of at least 30. All right. So we are doing a what percent confidence interval? 95% confidence interval. Uh-oh, my board is struggling here. I'm going to need to take a timeout. All right, let's see if my pen is charged up well enough to keep going here. All right, so we are finding a 95% confidence interval. Okay. So one of the things we need to know is the critical value for a 95% confidence interval. We already have that. We did that not too long ago. Right here, that's 1.96. Excellent. Okay, what else do we need? Okay, so we're estimating mu to be 15.6. But now we need to find the error. What's that error to create our confidence interval? Okay, so we have to look back at our error formula. The critical z-score times the standard deviation divided by the square root of n. Okay. Now recall n on this one is 90. Okay, so our error, critical z-score times the standard deviation divided by the square root of n. So our error in this one, 1.96 times our standard deviation was 1.8 divided by the square root of 90. So we get an error of about, grab my calculator. .37. Okay, so that's our error. Remember that this is our population mean estimate, 15.6. Our error is 0.37, so we could say up to 0.37 bigger or 0.37 smaller. So what we're going to do is we're going to take 15.6 minus 0.37 and 15.6 plus 0.37. And when we do that, what do we get? 15.6 minus 0.37, 15.23. And when we add, we get 15.97. This is our 95% confidence interval for the population mean. So we need to finish this with a sentence. And this sentence is going to be a good, strong statement that we can make. We are 95% confident that the population mean of her times jogging is between 15.23 and 15.97 minutes. Okay, I'm going to type that out here so you don't have to watch me try to write that. We are 95% confident that the true mean of her jogging times is between 15.23 and 15.97 minutes. That's a cool statement. That's a really cool statement. Okay. Now, could we be wrong? Could it not be between 15.23 and 15.97? It's possible. Okay. We're 95% confident that's in there. So we're saying there's a 5% chance that we could be wrong, that it's not between those two times. But we're 95% confident they're between. Okay. That's really cool. Now, what if this was a What if we wanted to be 99% confident? Think about what's going to happen to our range of numbers if we were to calculate a 99% confidence interval. Okay, should we do it? Okay, but before, I want you to think about what's going to happen to these numbers if we want to be 99% confident. All right, let's do it. I'm going to duplicate this page. So then I can just go through and erase things here. All right, so let's go with 99% confident. So that means our critical z-score is no longer 1.96. What's our critical z-score for 99% confidence interval? Right here, 2.575. So that means when we calculate our error, the only thing that switches is this 2.575, and we just made that bigger. So what's going to happen to our area if we increase that critical z-score? That's going to make the error larger. Okay, now the error is 0.49. So then we subtract 0.49 and we add 0.49. So now we have 15.11 to 16.09. So now our statement is we are 99% confident that the true mean of her jogging times is between 15.11 and 16.09. And I hope that makes sense to you. If we want to be more confident, what do we have to do with our error? What do we have to do with our range? We make it wider, right? Okay, I'm going to be more confident. I got to spread my range out here. Okay. Now there's only a 1% chance that we're wrong and the true population mean isn't between 15.11 and 16.09. So the more confident we are, the wider the range that we need. All right. So again, we're making, this is called inference, right? We're using a sample to make a statement about a population. A statistic X bar is a point estimate for the parameter mu. All right. So I think that's enough for today. I'm really excited about what we're getting into now. This is really going to start to be new stuff for you guys, and this is really powerful. Thanks for watching. We'll see you later.